The world of health information is it's massive. And it's so deeply fragmented. I
Hmm.
mean, think about it. On one hand, you have all this super granular data coming from your own devices.
Right, your heart rate, your sleep patterns, all of that.
And on the other, you have centuries of medical knowledge all packed into these dense, super specialized clinical guidelines. How do you even begin to build an AI that can connect those two worlds?
Well, that is the central challenge. It's this high-stakes problem that scientists working at Google Research and often collaborating with other institutions are really trying to tackle head-on.
And that's what this deep dive is all about. We're looking at this whole stack of AI models they've built to try and synthesize this landscape.
Exactly. And our mission today is really to unpack three key threads of this work.
Okay, so first up is the Advanced Clinical Assistant, AMI. That's AMIE, pronounced like the name Amy. And it's designed for managing diseases over the long term.
Then there's the Personalized Health LLM, or PHLLM. This one is all about your personal wearable data and turning it into something you can actually use.
And finally, we'll get into the open models, things like MedGemma under this umbrella called HAIDEF, which is all about giving developers the tools to build their own health AI.
A pretty big agenda.
It is. Okay, let's unpack this. I want to start in the clinic with AME. So it's built on these foundational models like Gemini 1.5 Flash. But if the goal is managing a patient's condition over months, maybe years, why a two-agent architecture?
Yeah, that's a great question. Because a basic LLM can, handle a conversation. It can do dialogue, but it often lacks that deep, structured reasoning you need for complex medicine. So AMI is split into two parts. You have the dialogue agent, which handles the user-facing stuff, the empathy.
The conversation.
Exactly. And then you have the really critical piece, the MX agent.
The MX?
MX, it stands for management reasoning. This is the part that does the sophisticated long-term planning.
So it's tracking the patient's progress.
It's monitoring their trajectory, personalizing treatment plans, and proactively making adjustments across multiple visits, which, that's the really hard part of primary care,
And to do that, it's using what they call deep context grounding.
which is a fancy way of saying is grounding its reasoning in current authoritative clinical documents.
The sources here mentioned it can reason across 627 clinical guideline documents at the same time.
Yes, things like the UK NICE guidance,
Hmm.
BMJ best practice. We're talking about a corpus of 10 million tokens of evidence-based medicine it can access instantly
So that's the engine. How on earth do you validate something like that?
with a very rigorous test. They ran a randomized blinded study, a virtual OSCE study pitting AMS against 21 human primary care physicians
Okay, so AI versus human doctors.
across 100 realistic multi-visit scenarios. The whole point was to see whose management plan was better over time.
And the result.
Pretty compelling. Specialist physicians who graded the plans rated AMAS as non-inferior to the PCPs in overall management reasoning.
So on par with a human doctor.
But here's where it gets really interesting. AMI was actually statistically better in the preciseness of treatments and investigations, and in how well it stuck to those complex guidelines.
Wait, hold on. It was better than actual trained doctors at following the rules, the documented best practices.
That's what the data showed. It points to a victory for AI's capacity for precise recall, when the task is just sticking to established documented rules, which is a huge burden on human memory.
The AI just does it better.
It can manage that complexity better.
Yeah.
And that consistency is super valuable when you move into subspecialty areas too, like with medications.
Okay, so they tested it on medication reasoning.
Yep, on a benchmark called RxQA, which is validated by board-certified pharmacists.
So this is high-stakes stuff.
Not just drug names, but interactions, patient history, all of it.
Exactly. And on the higher difficulty questions, AMIE actually outperformed the PCPs.
Wow.
And it goes further. They tested it on suspected inherited cardiovascular disease using multimodal data text reports from ECGs, MRIs.
Really complex data. And AMIE was rated superior or equivalent to general cardiologists across 10 different clinical domains.
That brings up a fascinating point, which is all about errors. What happens when the AI gets it wrong versus when the human gets it wrong?
This is maybe the most important takeaway. Their error profiles are almost inverted. They reveal these complementary strengths.
How so?
The analysis showed that the general human cardiologists, they were concise, they were specific, but 92% of their clinically significant errors were omission errors.
Omission errors, so they miss things.
They missed things. A key diagnosis, important finding, they forgot to recommend family screening.
And Amy Me.
AME was rated as thorough and sensitive, but its errors were mostly commission errors.
Meaning it suggested things it shouldn't have.
Basically, yeah. Suggestions of potentially unnecessary care. Mostly things like repeating a non-invasive test. So it's being overly cautious, overly thorough, rather than missing something critical.
So A&E adds thoroughness, and the human adds that specificity and judgment.
Exactly. And that contrast is huge for thinking about how you'd actually implement this in a clinic.
Okay, so we've seen how AI works in the clinic with all this institutional knowledge. But what about the health data you generate every single day?
Right, from your watch.
That brings us to our second focus. PHLLM, the Personalized Health Large Language Model.
And this is where it gets really interesting for the average person. PHLLM is basically a version of Gemini that's been fine-tuned to reason over that numerical time series data from wearables.
Like a Fitbit or a Pixel Watch.
Exactly. Focusing on sleep and fitness. Because trying to interpret weeks of heart rate variability in sleep stages, that's complicated even for a human coach.
So how do you benchmark an AI coach against a human one?
They built this data set of 857 long-form case studies. Each one combined up to 30 days of sensor data with analysis and recommendations written by a human expert.
So they could compare the AI's output directly to a human's.
And in the fitness case studies, PHLM's overall performance was not statistically different from the human experts. The p-value was 0.48.
Which, for all intents and purposes, means the AI is performing on par with a human coach at making these complex, personalized plans.
The implication there is scalability, right? You can get that kind of coaching without the cost or availability constraints of a person.
And its objective knowledge is solid, too.
It's exceptional. PHLLM blew past the passing thresholds on professional exams. It scored 79% on a sleep medicine question bank and 88% on fitness certification questions.
And how did that compare to the humans?
It actually surpassed the average performance of the human experts they recruited for comparison. They scored 76% for sleep and 71% for fitness. The model just has this deep mastery of the objective knowledge.
So it can bridge that gap between the raw numbers from a sensor and how you're actually feeling.
That's a key part of it. They tested its ability to integrate that sensor data to predict subjective outcomes, things that user reports like trouble being productive or tiredness, and the model could do it effectively, proving it can connect the numbers to the feelings.
But it's not just about the analysis, it's about the conversation, right? This led to an insight they called wayfinding AI.
Yes. In their qualitative studies, users really valued it when the AI would proactively ask clarifying questions.
Instead of just spitting out an answer.
Right. It's like how a good doctor takes a detailed history before giving advice. So they ran a study comparing this wayfinding AI to a baseline AI.
And the users.
They overwhelmingly preferred the wayfinding AI. They found it more helpful, more relevant, better tailored to their situation. It showed that for personal health, how the AI interacts is just as critical as the final analysis.
So we've looked at these really advanced custom models for the clinic and for personal coaching. What does all this mean for the wider community, for developers who want to build their own health apps?
Well, we're seeing this big shift toward open foundations. Google Research is opening up a growing collection of these models specifically for health applications. It's under this family called HAIDEF.
Health AI Developer Foundations.
Exactly. And this is where Gemma comes in.
Gemma is a set of open medical models based on Gemma 3, and they're available on places like Hugging Face. So the idea is developers get all this expertise without having to train a massive model themselves.
That's the key. The efficiency. Gemma's smaller sizes make it incredibly efficient to fine-tune, but its baseline performance on things like clinical knowledge, it's similar to much, much larger models.
And crucially, it's multimodal. It's not just text.
Right. The 4B variant can understand and reason over medical images, radiology, dermatology, histopathology.
The examples are pretty striking. It can look at a chest x-ray and accurately describe findings for something like a large pneumothorax.
Or identify basal cell carcinoma from a picture of a skin lesion. It shows real performance gains over the more generalist models on these very specific visual tasks.
So the big takeaway for developers is the power of customization. You can take this foundation and tune it for a really specific niche application.
And get huge results. For instance, they fine-tuned it for retrieving information from electronic health records and saw a 50% reduction in errors. That's a massive improvement.
So when you pull it all together, it paints a really detailed picture of the research coming from these scientists at Google Research and their collaborators.
It does. We've covered the complexity of longitudinal disease management with AME, the deep personalization you get from PHLLM, and now these open development tools like MedGemma. It's a really focused effort.
A focused effort to close that gap between the super specialized medical world and our everyday data.
Hmm.
So, as we wrap up, let's go back to that idea of errors. We talked about how even experienced human clinicians can make omission errors. They miss things.
While a specialized AI like AME trends towards commission errors, suggesting things that might be unnecessary.
So that brings us to the final thought for you to consider.
If the greatest benefit here is complementing human weaknesses, the AI adding that rigorous thoroughness, the human adding precise judgment and specificity, what comes next? What new protocols or collaborative interfaces are we going to need to make sure this teamwork actually works? To make sure we're harnessing both strengths instead of, just magnifying the risks of over-testing or overwhelming the patient with information. That, I think, is the real challenge as we start to bring these incredibly powerful tools into the real world.